So, good day, sir. I'm here to walk you through the PIT of this subject, which I developed using Streamlit, and this one is called the Enhanced Polynomial Regression Calculator with Full Math Breakdown. So, the goal is simple. It is to help users input data, generate a polynomial regression model, and actually understand the steps behind it. So, what makes this different from regular regression calculator is that it doesn't just give you an equation. It actually shows you how that equation is formed from matrix creation to solving for the coefficients with all the calculations visible. So for today's demonstration, I'll be using a simple data set where x values ranges from 1, 2, 3, 4, and 5. Control Enter. And now for our y values, we have 2, 5, 10, 17, and 26. Control Enter. So when you look at these values closely, you will see that the pattern looks nonlinear. So it gets steeper, which means a straight line won't fit it well. So we'll try a polynomial regression instead. So the first section of this calculator allows us to input our data here. So you can either type it manually or we can also upload a CSV file here. So this time I'll just manually enter the datas or values so we can see them clearly. And after entering the data, I will select a degree of the polynomial. So we can just click this and drag this and up until 6. But since we suspect this pattern is quadratic, I'll choose degree 2. So this means that the equation we're trying to find will be in the form y is equals to ax squared plus bx plus c. So now, once I click Analyze, the app builds the Vandermonde matrix here, there. So the app builds the Vandermonde matrix. This matrix is essential in polynomial regression because it transforms our x values into powers based on the polynomial degree. And since we chose degree 2, each row of the matrix contains the x squared, the x, and the 1, which represents x sub 0. So for example, here in our first row, we have 1, 1, 1 values, and our x is equals to 2 is have the 1, 2, and 4, and so on. We can click this to see the full screen of the matrix. We can even download this one. We can even search for it. And next one is we form the transpose of A, which is the A to the T, the matrix product, which is the A to the T times A, and the vector product, which is the A to the T times Y. So this allows us to solve for the coefficients A, B, and C. So here in the transpose of A, which is A to the T flips rows to columns, which enables us to form symmetric matrix equation. So as you can see, it just flipped from these values. It's now here in our columns, the row which is here. So you can see the values here. It's here. Now for our matrix product, A to the T times A shows how each column of A correlates with others, which is important for coefficient dependency. So here is the step-by-step for ATA so we can understand how it was computed. So let's try to show it in a full screen. This is the first column. Wait, we can show the values. This is the first row and the first column we have 5, how it was, how we got into 5. The second one, 15, 1 times 1 plus 2 times 1 plus 3 times 1 plus 4 times 1 plus 5 times 1. Here, 1 times 1, 4 times 1, 9 times 1. This is a matrix calculation to the values we got here. The A and the AT. There, AT times A. So that is for the matrix product, and for the vector product, which is a to the t times y, this is the computation we have. Here is the AT, as you can remember this one, and times it to our y values. So 1 times 2, 1 times 5, 1 times 10, 1 times 17, plus 1 times 26. Here we have 60, 240, and 1034. So you can just click that to make it disappear again. So we can also click here for a full screen, or we can download it as well. There, download as CSV. Wait. So next is our solved coefficients. So solving a to the t times a times a is equals to, or this is the coefficients, this small a, and is equals to a to the t times y, which provides the exact best fit coefficients using linear algebra. So a times your a1 and a2, we have the value 1, negative 0, and 1. So this is our polynomial equation. We have y is equals to, wait, our decimal is up to 4 decimal numbers. So 1 x to the 0 plus negative 0 x to the 1 plus 1 x to, or 1x squared. So next is the calculator now will generate a graph, which is this one, the curve behavior. So you will see that the red dots, these are the original data points, and the blue line is the regression curve. So in this case, all dots lie exactly on the blue curve, meaning we have a perfect fit. So the graph updates in real time. So if you change the degree or data, you will immediately see the curve adjust. So this helps users understand the shape of different polynomial degrees. So there you can see the exact data points as we over our cursor, following the regression curve. So x and 26, it matches our data. Our x is up to 5 and our y is up to 26. So another useful feature is the ability to compare the regression output with a custom function. Let's go back here. This one, compare with custom polynomial function. So we can manually enter any expression in terms of x. Let's try this one. So after clicking that one, we will enter our polynomial. So I'll type in x2 plus 1. So since we already know our equation follows this, we will click enter to apply. And we will then analyze. So it's just the same, but this will overlay this function on the graph. earlier we don't have these broken lines, right? So we have this feature in order to compare the regression output with a custom function. So as we can see, this is the user function or the custom polynomial function that we entered earlier. It does here, it confirms our model is accurate since it lies there perfectly. So here we also I also included a residual error plot to visualize prediction errors. So residuals are the differences between actual y values and predicted y values. So in this example, all residuals are zero, meaning there's no difference between what the model predicts and the actual data. So this makes sense because our data set fits the equation perfectly. So this also provides a behavior summary of the curve, this one. So since our polynomial degree is 2, we know the graph is a parabola. And because the leading coefficients a is equals to 1, which is positive, the parabola opens upward here. So this kind of curve shows accelerated growth, which you can see in the way the y values increase, slowly at first, then more rapidly there. And then it finally provides us the equation in code format, this one, exportable equation. So you can copy and paste this into a Python script or calculator for further analysis or plotting. So now let's go back and let's try this one. If you prefer to upload data instead of typing manually, this calculator also accepts CSV files. So here I made a CSV example with the same values, and let's erase this one. Control enter. Let's erase this as well. Control enter. Oh, and let's keep it that way. Now let's browse files. This one, numerical method CSV file example. So here we can attach this one and let's try to analyze again. So let's try not to compare with a custom polynomial function. So as you can see, it we didn't have a data that was manually entered here, but since our CSV contains the same values, it reads what's inside of that CSV. So it's still the same because I made it or included the same values. Let's try to there. It's just the same. So now to conclude, this not only performs polynomial regression, but also breaks down the entire process so that users, especially students or researchers, can understand why the curve fits the way it does. So it bridges the gap between theory and application by showing the exact matrices and solving steps, not just the final equation. So this one makes a great educational tool, especially in subjects like numerical methods, linear algebra, or machine learning. So thank you for listening, and I hope this demonstration gave you a deeper appreciation of what polynomial regression looks like under the hood. So thank you for watching.